fun about home ec and stuff, but not during chemistry. Okay, so we're going to talk about the particle wave duality of matter and everything. This is on the back of that half sheet. That's why I said pull that out. You will not be writing down most of this. You'll be writing down very little of this. Okay, so maybe highlight some of the things that I say are important with stars next to them. So the quantum mechanical model indicates that electrons they have multiple personalities, okay? They also talk about how matter can act like energy. Remember way back in the day we were like, matter is matter and energy is energy and there's no crossover, right? We said energy didn't have mass, didn't have volume. Well, when you get on the scale of the size of the electron, they actually start to interact more. Yeah. So we call that the particle wave duality because the particle indicates the matter side of things and the wave indicates the energy side of things. So we're saying how matter actually does have a wavelength that it kind of puts off, or we're saying how an electron can have a mass. Well, we already knew that because energy is just straight up electrons sometimes, and it has mass. There's more to it, and I'll show you the video on it. But that also feeds into Heisenberg's principle, which we talked about yesterday. That was my awesome joke. What was it? What did it relate to? We know the velocity or the what? Location, but it's hard to know both. And that's because of the act of observing the electron, or anything for that matter, kind of decides its fate. And so it's bigger than us, okay? We just need to know some of the background. Anyway, so back to Schrodinger. He said electrons are quantized, so they have a set energy, but he also said that they don't have a specific path. So like Bohr said, if they have a specific path and they have specific energy. This whole I don't have a specific path relates back to Heisenberg's principle. We know it's energy, but we don't know exactly where it is. We think it's in this general cloud area. So I might draw a cloud and we'll say electrons are here, 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 but they have some area to play. So that's where Schrodinger brought into the model the electron cloud, also known as orbitals. Remember orbits versus orbitals. Orbits were Bohr, orbitals were Schrodinger in the modern model. So it's hard to just say, oh, it's in this area. It's nice if you have an address. Like, okay, we live in Concord. Yeah, some of us Charlotte, but we live in Concord. It's a big area. So you're like, oh no, I live in north, south, east, or west Concord. I live near downtown, or I live here. It's kind of narrowing it down, but then you can even go narrower. You can say, I live on Union Street, and I live at 400 Union Street. So you can narrow down the location. But even at that location, if you live at 400 North Union or something, maybe you're in that house, but we don't know where you are in the house. So I'm in like the bedroom on the left, right? So you can go narrow, narrow, narrow to really specify the location. Well, that's kind of what these quantum numbers do. So these numbers that are printed on your sheet specify the exact, I use that term loosely, right? As most specific as we can get where the electrons live in that big electron cloud. The big electron cloud is like Concord. We can narrow it down though. So the first number, there are 4 digits to be like the electron's address. Are you with me so far? We're taking numbers and we're assigning numbers to indicate kind of like the address of the electron in the atom. So the principal quantum number is saying I live in this general energy level. And the energy level can be like n equals 1. Well, that's the first energy level. N equals 2. That's the second energy level, and so forth. So which one is closest to the nucleus? Energy level 1. So that's kind of like fairly close to the nucleus, a small cloud. The farther out you get, energy level 2, 3, 4, 5, 6, 7, that gets to be a huge electron cloud. So this energy level, n equals 1 through whatever, is going to also indicate the size of the neighborhood, the orbital, the cloud. So that gives us some information about how big of a radius we're really looking at here. Because the bigger the radius, the more area the electron has to play. The second quantum number is called a sublevel number. Okay, so it's kind of like giving us a little bit more indication that everything in the world is 3D. Right? Even a piece of paper is 3D. It has a thickness to it. It's 3D. So we look at things on the axis of, I'm going to label this X, Y, and Z. And so we can look at things on a 3D model. So the sublevel sometimes is going to indicate the shape of that orbital because some of the shapes differ. Sometimes the shapes will look like a sphere, like this, a 3D sphere. Some of them look like a dumbbell. Some of them look like a double dumbbell. And some of them look like a flower, a bunch of little loops together. Okay, so they change their shape, but of course these are all 3D. Now, instead of saying, oh, the flower-looking one, we call it F. Instead of saying the double dumbbell one, we call it D. Instead of saying the single dumbbell one, we call it P, and we call the spherical one an S. That's what these letters are. We're going to see those letters a lot in electron configurations in our next couple slides. So the sublevels have a shape. The spherical one is S. That makes sense, right? The dumbbell, single dumbbell, is called P. The double dumbbell is D. Okay, so double dumbbell, I think of two dumbbells together like this. And then the flowery looking one is F, okay? So I try to come up with the names of those shapes to indicate, to correlate with the letters of the orbital. Now, tell me again, what is the significance of an orbital? It's where what? The electrons are, right? So if you say you're in the S-shaped orbital, we know you're in this general area. If you're in the flower-shaped orbital, you've got a lot more playroom because you're a bigger, broader orbital. Okay, now that we kind of know where you are in relation to the nucleus and then like exactly which orbital you're in that area, then we can go farther. We can say, okay, well, so there's actually more than these 4 orbitals, okay? If you're in the S orbital, you have to be in the sphere. If you're in the P orbital, you have 3 different P orbitals you can live in. You can live in the P orbital that goes up, sideways, or in the z-axis, I want to say, kind of into the board and out of the board. It's got 3 different orientations. That's what I'm saying. So the P's come in 3 varieties. And so you might be in a particular orbital, the one that goes up and down, or you might be in the one that goes this way or inside and outside the board. So that's what this next quantum number tells us. And we're not going to assign the quantum numbers. I just want you to be aware of the fact that we can narrow this down. The D's, so, and I'm going to kind of label back up here. There's only one S orbital. So if you're in the S orbital, you're in the S orbital. If you're in the P orbital, you have 3 options because they come in 3 different orientations. If you're in the D orbital, you have 5 options. It can be like this way, or this way, or this way, or this way, and then there's one that looks like a donut. Okay, I'll show you on the next slide. So do you see what I'm going up by each time? So what's the next one? How many different orientations of F are there? There are 7 different orientations of F. So flower, just think flower can be like this way, or this way, or this way, or this way, this way. There's lots of different orientations it can take in space. Okay, so now that we narrowed down what your orbital shape looks like, which specific orientated orbital you're in, then we can say, okay, the rule of thumb is that, so here's that right there. The rule of thumb is that per orbital, there's only 2 electrons that can exist in that orbital. So I'm going to put 1 electron here and 1 electron here. Well, if electrons spin the same way, think of 2 negative objects spinning the same way. They create a huge magnetic field just because they're negatively charged. If they spin the same way, it kind of makes everything off balance because everything's kind of moving one way, all the negatives over here, all the positives over here. It actually needs to be more balanced. So do you think they should be spinning the same way or opposite ways? Opposite. And it helps create some more balance and less repulsion and stuff in the atom. So this electron's going to spin up and this electron's going to spin down. Okay? So what we're doing now is assigning which electron we're talking about, the one that's spinning up or the one that's spinning down. And that's the 4th quantum number. A lot of times we call it clockwise spin or counterclockwise spin, but I just draw an electron spinning up and an electron spinning down, and that indicates the same thing. They're just opposite directions. So this is really dry, but this is important to know at least some of the significance before we talk about all these letters and numbers again in the realm of electron configurations. Okay, that's the reason we had to talk through this. I do not expect you to memorize all of this. I need you to understand the significance and meaning behind it. Okay, do not memorize these things. The only one that I really think that you're going to see more often is this word, the principal quantum number. It just means N, or energy level. That's the one, put a star next to it, because that's a term you'll see. Okay. So, electron configurations. What does it mean to configure something? Or what's a configuration? Say it again? How it's placed. So the configuration of my room right now are long rows of pairs. Okay, another teacher might have a configuration that's all single chairs. Just means the arrangement in space. That's all we're talking about for electrons. So, these are those S, P, D, and then F. F has some funky looking shapes, but you see there's 7 different orientations. There's 7 pictures. So that's all those pictures are again. Okay, so have we seen pictures like this? Yeah? Those are the old style orbital diagrams you've probably drawn in middle and maybe biology. So that's how we used to draw them. You're like, oh, there's 2 electrons in the first energy level, there's 8 in the next one, and so forth. We do not draw them like this, because guess whose model this is? Bohr's. And Bohr's is wrong. Right? This is not correct for anything other than hydrogen. So we cannot draw everything like this. It's nice to go back there, but whoever did this had to kind of get you through so you can make it to the next level, but I'm just telling you right now that it's a lie. Okay, so it's a lie. We're going to fix this lie right now, okay? So our essential question is figuring out how electrons are arranged, and we're going to use quantum numbers to describe that. So there are 3 rules that tell you how electrons can be arranged. These are the 3 rules. If you need to write these down, write these down. I'm going to try to go slow, but if you guys get this and you pick up on it quickly, let me know, because I need to figure out how much practice I need to do. And if it's less, it's less. If it's more, it's more. You just got to talk to me. Oh. Who is... Who's Kate Allen's baby? Oh, all right, popular baby. Take good notes from her, please. She actually over there. Okay, so 3 people obviously were involved in making these rules, and their names are here. Off-ball, he stated that electrons have to enter in the energy level that is lowest, or that means closest to the nucleus. First, what energy level is that? N equals what? 1, right? Then that's like, duh, it makes sense. All right, we're starting at N equals 1. We're not going to just be like, hey, I think I'm going to put this in N equals 5. It makes sense. So how do you remember off-ball did this? I came up with some stupid stuff that you're going to have to latch onto or make up your own. But off-ball starts off awfully low. Okay, this is me telling you how to remember the person and the rule. He starts off awfully low, lowest energy level. Pauli came along and said, oh yeah, that's great. We're going to start the energy level. And we're going to start putting these electrons in these little orbitals and these flower-like shapes and all this stuff. But how do you remember how many go in there? Pauli decides that a pair goes in. Pauli pair. Okay, Pauli pair means 2 electrons. That's it. Can go in any orbital. Because you got to know the name and the rule. They go together. And then Hun came along and said, oh yeah, but as we fill up these orbitals, electrons and electrons, what do they do to each other? They're both negatively charged, right? What do they do to each other? Repel each other, right? They don't, so that's really, really a stressful environment to put 2 electrons right next to each other. So Pauline's like, well, but I know that, but 2 electrons can go in an orbital, that's how we fit. But Hun said, no, we need to fill up each orbital with 1 electron at a time, and then if we have to go back, we'll refill it to make 2, 2, 2. So I call that Hun's ones rule. Okay, Hun's ones rule. So if you have to memorize it, Hun's ones rule means 1 electron goes in an orbital at a time. Pauli says that at most there's a pair of them, and off-ball's like, don't forget, you got to start off awfully low, and we're going to start off the lowest energy level and go up. Okay, so hopefully that will help you remember the names and the people with their rule. Okay, so I'm going to define what orbital and suborbital is whenever we get there, but these are important. Now, an orbital, the way we draw an orbital, yeah, I showed you like there's an s orbital and a p orbital and a d orbital and a flower orbital, okay? I showed you to draw that, but that just takes too much nonsense to draw every time. Here's how we draw an orbital. A line. That's an orbital, okay? How many electrons fit in there? 2 electrons fit. And how do they spin? Opposite. Up, down. That's how we draw 1 orbital with 2 electrons in it. Because, I mean, that's cool and stuff to draw the orbitals, but that's how we draw it. Okay? That's 1 orbital with 2 electrons. Okay. So let's draw them and talk about what these numbers mean again, okay? So whenever you're writing out an electron configuration, you use all these numbers and letters in superscripts. So you have to know what each of these little things mean. So like maybe write out this right here and then point to what each of these letters mean. So when you're describing it, the very first number, the coefficient-based number, represents the energy level that this electron is filling as it's filling up the orbitals of a particular atom. The second thing listed is the letter. And what are the four letters we've seen? S, P, D, F, right? So that's what the second one is. And it's telling you the type of orbital, the shape of the orbital. So it's more like this shape. And then the last exponent-based kind of superscript is telling you the number of electrons in that orbital. And so we're going to see numbers like 1, we're going to see numbers from 1 to 10. But, like I said, in the s orbital, there's only 1. So if you have an s, the maximum exponent you're going to have is a 2. If you have a p, how many different p orbitals were there? 3. So what's each of those orbitals holds how many electrons? 2. So how many total electrons are there? 6. Or it can hold up to 6. So you're going to see the p max out at 6 because there's 3 of them, each holding 2, 2, 2. So then the d orbital maxes out at 10 because how many orbitals are there? 5 of them. So what do you think the f maxes out at? 14, right? So if you're writing numbers above 2, 6, 10, and 14 for individual orbitals, it means you've done something wrong. And I'll show you how to track this. Oh, pull out your periodic tables because you're gonna see it's a very good tool for this. So let's start by adding up the electrons for a particular. Let me do an easy one first. Okay. So I want to do the electron configuration for beryllium. Okay. Beryllium is here. Beryllium is atomic number 4. How many electrons does it have? 4 electrons. So we only have to track 4 electrons, where they are in the energy levels and the orbitals. So on your periodic table, on yours, if you have one with you, hopefully you do, I want you to do yourself a favor. Before we move on, I want you to label that the first two groups here are called the S block. Okay, or just S. That's all of this. All the first 2 groups. Skipping over to groups 3A through 8A are P block. Okay? And that's because their electrons fill the P orbitals. Anybody in this group is going to have, actually anybody anywhere can have P electrons in it, but these specifically end on a P electron. So everything in this group, you know, groups 3 through 8. Everything, I'm going to erase my little beryllium mark there, okay? Everything in the transition metal category, right here, groups 3B through, what is this, 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, 10B. They're all D block. Okay, they're the block of the D electrons. And then, finally, we get down here to the bottom, which is that excerpt from the periodic table. It's called the inner transition metals, and they're F block. And electrons fill sequentially, like they fill up one at a time, you know, and they build these different elements. So we're going to be going across the periodic table like you're reading the periodic table from left to right. So if you're here, you're going to say, I'm in the first energy level because I'm in period 1. So you're at a 1. What block are you in? For hydrogen specifically. You're in S block. How many electrons have I filled? 1. That is the electron configuration of hydrogen. 1s1. So it's saying I have, for hydrogen, I have 1 electron. It's in the first energy level in the s orbital. And we know that helium is not exactly a noble gas. It is a noble gas in some extent, but I'm actually going to put helium here, really where it belongs, next to hydrogen. Okay, so if I want to talk about helium, then I would say, okay, I'm in the first energy level. I'm the second one over, though, right? So I'm still in the S block, so I still have to write an S, but I'm the second one over, so that means I filled up 1 electron, 2 electrons. So overall, how many electrons does helium have? 2. 1s2. That is the electron configuration of helium. Okay, let's go more. Now we need to go to lithium. How many electrons does it have? 3. So I want to write this one kind of higher. I have to start there at the top. Okay, starting here, I go 1s2 because I have to fill up both of these electrons through hydrogen and helium before I can go all the way. Okay, done with that one. Now I'm here before I can get to lithium. So before I get to lithium, I've already gone through 2 electrons. So how do I count for the third one? I'm no longer in the first energy level. I'm in the second energy level. What block am I in for lithium? S. How many electrons over? Just 1, because I'm only 1 electron into S block. Because the S block, again, only holds 2 electrons the whole time. The max exponent you're going to see for S block is 2. So 1s2, 1s2, 2s1 is the electron configuration for lithium. It builds, right? So if I wanted to go all the way over here to zinc, I have some talking to do, right? I got to go through all of these rows until I get here, and then I get to finally talk about zinc. That's because zinc has how many electrons? 30 electrons, right? Because it's got a 30 right there. So you got to talk about every single electron. Okay? So we're gonna work through some of these. But it becomes easier because you start to group things together, and I'll show you how that works. So let's go ahead and do zinc. Okay? Yeah.
How did you move helium?
Because helium is actually it resembles hydrogen more than the noble gases. It actually should be grouped over there, but because it has octet or its full outer shell, it sits here. Just assume that it's next to hydrogen though. Helium does not have p electrons whatsoever. It only has s level electrons, a very simple shell.
So is that the only one?
That's the only one. Yeah. Yes, ma'am.
So I'm just confused. Why don't we have 1s1?
Because 1s1 and 1s2. When you say 1s2, you're accounting for 1s1. Because when you say 2, you're talking about both of those electrons. Instead of going 1s1 and then another 1s1, just say 1s2. You group them. Okay, so I'm going to erase a little bit so I have some space, and then I need you to write 2 more caveats on your periodic table. When you get to D block, and you get right here, normally, like at this energy level, what energy level would potassium be sitting at? 1, 2, 3, 4, right? So here you would go 4s2, correct? 4s2. But when you hit D block, you have a rule called N-1. What does N mean again? Energy level. So that 4s2 that you just wrote is true until you get here. Then you have to go N-1, so not 4 but 3. And then what block are you in? D, whatever number. If I ask you to go to chromium, then you go 1, 2, 3, 4. You'll put a 4 right there. So that's one rule. When you get to D block, you do N-1. When you get to F block, you do N-2. And we'll do some examples with that too. So that's everything you basically need to know about periodic table. And now let's practice, okay? So for the electron configuration of zinc, that requires us to go through a lot of information on the periodic table. I'm going to give myself some room here. I'm going to erase mine a little bit, and you guys can yours. So I need to start here. Remember, helium is here. So I need to go through the first row. So what was that again? 1s. 2, if I'm going all the way through, okay? So 1s2. Now I'm done with the first row. Now I'm on the second row. So how many do I need to go through? 2. What block? S. How many electrons? 2. So that's 2s2. We go all the way over here. Oh, now we're in P. We haven't done a P yet. So I'm still in the second energy level. What block am I getting ready to enter? P. And I need to go all the way through it. How many electrons? 6. 2p6. Okay? Now I'm down here. See, I'm just going across. I'm down here, so tell me what I write. 3. 3s2. Okay? Now I'm scooching through here. Give me this. 3p6. Because there's 6 electrons there. Okay, so we're just lumping them. How many electrons have I accounted for so far? Add up the exponents. That's how many electrons I've accounted for. 18. Sounds good. Guess what I'm at? Argon. 18. Right? That's right. If I stopped right here, that's the electron configuration for argon. Okay? So if that's the electron configuration for argon, what's the electron configuration for chlorine? Make a guess. 3p what? 5, right? So I would have to just truncate a little early. Like I don't go all the way through. I stop at chlorine. I'm like 3p5. And if you need to double check yourself, you just say 2 plus 2 is plus 6 is 10, plus that is 17. 17, chlorine, yay. Okay, so what if, listen, let me keep going. Let's go through zinc like I wanted to. So that was 3p6. I'm all the way through argon right now. Give me back here. What is this? 4s2, and then for D block, I told you to go all the way through zinc, but what do you do special? -1, so 3D. Say again? 10. How many electrons should that add up to? 30, because that's zinc's number. It's like a puzzle, right? You got to put it together. But we're gonna go through some more practice to make sure that you're comfortable with this, especially when you get to F block. Yeah.
Where is the N-1?
The N-1 only applies, this is a rule you have to remember, only applies when you hit D block, which is this barrier right here. So when you're starting to go across and you hit D block, go, oh, need to take my original row and -1 from it.
Where did you do that?
I did it right here. I went from 4s2 and I dropped it to 3. Yep. Sarah.
Oh, so then what would the electron configuration be for like gallium or whatever?
Gallium.
Where
Okay.
did the
So, oh, good question. Yes. So once I hit that barrier again, I'm back to my normal. So it's now blah 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 3d10. Back up. Let's do germanium. Okay. So hit me right here. 3d10 what? 4p2. Okay. So let's do some of these. You guys kind of see the trend here? Okay. Let's do a couple easy ones, and then we'll come back to do orbital diagrams. Let me choose. Okay. I want you guys to do. You guys do sodium. You guys do sodium right now, and then we're going to do tungsten together. So I think tungsten is lower. Hold on here. You guys do sodium out loud for me, okay? Tell me what you got. Shout it out. 1s2, 2s. Sodium? 2s2, because that only gets us to beryllium, right? Okay, keep going. 2p6, that gets you all the way through who? Neon. And 3s1. Good. 3s1 stops you in the middle of S block at sodium. How many electrons should that have? 11. How many electrons does sodium have? 11. So what you were describing literally is where every single electron is in sodium. It has 2 electrons in the closest energy level to the nucleus in the s orbital. It has 2 electrons in the second energy level in the s orbital. It has 6 electrons in that little flower-like, not flower-like. It has 6 electrons in its p orbitals, and there's 3 p orbitals. And then it's got 1 electron in that third energy level of s. So you're describing it in number form versus drawing these pictures out. Okay? But we do need to draw pictures in that orbital form like I showed you earlier. So let's go ahead and do that now for sodium, and then we'll do tungsten. So it's so easy to draw the orbital diagram once you have your electron configuration. So underneath here, write a dash and write 1s under it. How many electrons are in the 1s orbital? 2. 1 goes up, 1 goes down. Done. All right. How many electrons are in the 2s orbital? 2. Guess what? 1 goes up, 1 goes down. We've accounted for 4 so far. I just draw mine as lazy arrows or half arrows. You can do the same. It's fine. P is where it comes into play. A little different. We have a PX, which is in one orientation, a PY, which is in one orientation, and PZ, which is in another orientation. It's just showing you the 3D area of it. So you literally have to draw 1, 2, 3 orbitals and label them 2p. You don't have to label them 2x, px, py, pz. That's AP level. But you do need to label the 3 orbitals that are collectively 2p orbitals. So how many electrons total? 6. So I know all of them are going to be filled, but whose rule we're going to follow if we go one at a time? Hund's 1. So you're like 1, 2, 3, and then poly pair, 6. Okay? So you do that in practice. Force yourself to do it one at a time, because when I trick you and I go, oh, it's only 2p3, then you got to go 1, 2, 3, not 1, 2, 3. This is wrong. This is right. Okay, so don't let yourself get lazy and be like, I totally will remember that. Yeah. Okay, last orbital, call it what? 3s, and how many electrons? Just one. And that's because you're looking at this exponent up here, and you're just drawing one orbital. So this is called the orbital diagram for sodium. Yes, ma'am.
How do you know which way it's bending?
If you draw one of them, it doesn't matter. I always draw the first one up and the second one down. So as long as they're opposites, we're good. Okay, so that's the orbital diagram. This is the electron configuration, but you see that they are definitely related. Okay, so let's do tungsten. Where's tungsten at? What atomic number? What atomic number? W. It's W. Sorry, this is tungsten. My bad. 74. Woo! Doggies. We got 74 electrons to count for. Okay, let's do this. Quickly tell me across. You should be tracing or here. If I pull up this stereo cable again, I can try to write it on here someplace. Okay, you guys tell me tungsten and start. Ready? We're going here. 1s2, 2s2, 2p6, 3p6. So you got me all the way through argon. Okay, keep going. 4s2, 3d10 because you hit D block, so you subtracted 1. Good. When you got to P block, you went back up to the 4th energy level. So that's 4p6. Keep going. Okay, so 5s2 and stop. Oh no, you're good. Keep going. 5s2. 4d10. All right, stop right now. How many electrons should we have? 48. You see where we stopped? Double check. 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is 10. That's 20. 30, 36, 38, 48. Good job. All right, we're at 48. Let's keep going. 5p6 because you jump back up to the 5th energy level. Keep going. 6s2. Okay, stop here for a second. This is the part I've not told you about yet. Where in the heck does F block come in? Do you just keep going? No. Do you notice the numbers for lanthanum and actinium? 57 is what it says here. It says 56, 57, and they go 72. What the heck happened, right? That right there is where F block fits in, because F block starts off with 58. So put a star, and I'll let you guys do it the way my periodic table is listed here. Does yours have 57? Yeah, okay. Put a star right there after 57, and put a star at the very, very first row of F block, because it should go 57, 58. And then do the same thing for the row beneath that. For actinium, which is 89, put a star after that. And then put a star in front of 90, which is thorium. Think thorium on F block. So basically, where those stars are when you're going to stop and insert all of F, that row, and then go back to hafnium. Like, for example, you end up 71 over here on F block. You're going to start back at hafnium. So that's what I'm going to show you right now. Okay, so we got all the way to 6s2, right? What is lanthanum going to be termed then, if you're continuing with our trend? Because you get 6s2, and then the next thing would be 5d1, because it's just 1 for lanthanum. Okay? Then you need to stop and go, let's go finish the entire F block. Just that first row, actually. So that would be not 5, but it's the original N. Sorry, good point. This is a 6, this is a 5, this is a 4. Okay, because it's 6 minus 2 is 4. So we're at 4F. How many? Should be 14. Remember I told you 7 times 2 is 14. Okay, so that's 4F14. And then we go, okay, we're done here. Go back up to D block. And that's 5D 1, 2, 3. Because you see it's 3 over from that. Okay, so 5D3 is tungsten. But you'll probably look back and realize we have a 5D1 and a 5D3. Well, what does that collectively make? 5D4. So if you write the 5D4 here, or like this separately, I'll get it. Okay, that's a hard part because sometimes the periodic tables have this lanthanum. Sometimes they actually have it down here. So it really depends on which one you're using. Okay. Take a stretch break for a second. So you guys are falling asleep. Get up. High five somebody. Okay. Woo! Let's get hype. You're learning the magic of where the electrons exist. You okay? Are you picking this up a little bit? Where are you at? Tell me what you're feeling. Or what do you do? Do you get where we're getting these numbers?
Huh?
Do you get where we're getting these numbers? This part? The big number? Oh, and it's the number, it's the period number. So the coefficient is like period 1, period 2, period 3, 4, 5, 6, 7. Okay? So that's what we're getting the first number. And it's the what? How many elements you have? Yes. So if you go all the way through this first block, that is 1, 2, 3, 4. So that's 4, the fourth energy level or fourth period. In S block, because that's what S block is, S, and you're going to 3 elements or 2 electrons, because every element builds 1 electron. That's really a big difference between elements, right? They have different number of electrons and different number of electrons. So as you build those electrons, you're noting it as you go. So there were 2 that came from the 1S energy level. There were 2 and then 6 more that came from the second energy level. And because every element has 1 extra electron. So to build tungsten, you have to get a total of 74 electrons, and they build from energy level to energy level to energy level to energy level. But how do you build? Exactly like this. 2 electrons go in the first energy level. A total of 8, 2 plus 6 is 8, so 8 electrons go in the second energy level. A total of the next one, 8 here. But then we have to go to the 4th energy level before we go back to fill up the rest of the 3rd energy level. It's called off-ball's rule because off-ball said you fill it in this exact order. So instead of memorizing that order, like who's got time to memorize that order, I use the drum table to show you how to track it. So we're going to skip a row to the next row. Is that where you're seeing you're not getting it or what?
How do you place it?
How do you what? Like
The one, the periods.
So the first, the number of period, and then like if you fall in this category, you're S. If you fall in this block of D, if you fall in this level, you're P. If you fall in this level, you're F. The letters don't change numbers unless you are, doing the whole minus 1. Let me do another example, okay? And try to write it down or something, okay? All right, guys, come back to me. Come back to me. Let's go. Let's finish this up. Oh, we've got to do the orbital diagram for this. Of course we do. Okay, so how about we talk about the orbital diagram for this? Let's talk about the differences. So let's just do it for the last bit. Let's just do it for 6s2, 5d, 4, 4f14. Deal? Deal. Okay. So what did I just say? 6s2, 5d, 4, 4f14. All right. So how would the orbitals look for this? What does the s orbital look like? Yeah, but we draw it like a line, right? All right, there's a line. 6s. How many electrons? 1, 2. How many orbitals do I draw for the d block? 5. Because I have a total. I know I only have 4 in this one. I know. Yes, but we need to draw all 5. But I wrote this differently. I'm going to shift the way I wrote this because it needs to follow through Alphal's principle. 4f14, 5d4, I think is what we saw. Yeah. Okay. So scooch back, rewind, 30 seconds. All right, guys. How many orbitals do I draw for F? Orbitals. I don't draw 14. I draw 7, right? So we can draw 12, 14, 16. Okay. So these are 4 f orbitals. Is that at 7? Yeah, okay. How many electrons are there? 14. 1, 2, 3, 4, 5, 6, 7. Dun, 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 dun. Okay, there's 14 there. All right, and then how do I draw the D's? 5 orbitals wide. Label it 4D, 5D, sorry. And then how do I fill the electrons? Whose rule? One's rule. So 1, 1, 1, 1. Any more? No. Okay, so that's how the tail end of tungsten would look. Okay. Let's give me on a scale of 1 to 10. Could you do this long electron configuration for pretty much anything? You feel like as long as you follow the periodic table. 10 being I'm awesome, 1 being I'm almost there, and then there's stuff in the middle.
1.
I just need to see where we are. All right, so I got 2 different ends of the spectrum. Let me do one more. That's a little different, so that we can practice, but also learn something else. Yes, ma'am.
I have a question. When you write the orbitals, does the order matter? Like,
It should follow the same order as the electron configuration, because that's going off Hall's rule. Yes, ma'am.
so before it had said 6, but you only had, I got confused because it had said 5 on one of them and 6 on the other. For the 6, you only have 1 back, but for the 5, you have 5.
Because it's not about the 6 and the 5, it's about the letter. If you have an s orbital, you have 1 orbital. If you have a p orbital, you have 3. Because it's, and I'll explain that terminology. The p orbital has 3 sublevels. Oh, no, I just lied to you. The p sublevel, I'm going to use this correctly. P sublevel has 3 orbitals, because the orbitals are that little line that we draw. So the p sublevel has 3 of those lines. So in your concept 5, it'll say like at this sublevel how many electrons are there. That's the letter, and then the number of orbitals in it are differ between s, p, d, and f. So the number of orbitals are the different orientations we're talking about. And let me continue, because I think we'll answer some more questions as we go. But I need to do this for ions as well. Okay. So ions have lost or gained what? Electrons, right? So we're all talking about electrons the whole day today. How many electrons has magnesium gained or lost? 2, okay? So we lost 2 electrons. Before it lost electrons, so what was its electron configuration? Go. 1. You can't look at me. You gotta look at the periodic table. 2p6. That's it's just 3s2. Yeah, sorry, I don't have my periodic table in front of me. How many electrons does neutral magnesium have? Just straight up magnesium. How many electrons does it have? 12. How many do we have here? 2 plus 2 plus 6 plus 2 is 12. Okay. Which 2 electrons do you think it lost? Huh? Think of like last one hired, first one fired. Yeah? Last one put on, first one's to go. Which ones are the last ones put on? 3s2. So 3s2 are the electrons that are lost. So what is the electron configuration of magnesium ion? Just this. 1s2, 2s2, 2p6. Who does that resemble? Which element does magnesium have the electron configuration of? Neon, okay? Note this. The ions form to have the electron configuration of a noble gas, okay? You want to be like the cool kids, like the noble gases, okay? Noble gases have a full, complete set of octet of electrons. They are in this very stable, happy zone, okay? So anytime something loses or gains electrons, it does it because it wants to look like the electron configuration of a noble gas. How do I know this is neon? Because how many electrons are here? 2, 4, 6, 6, 4 plus 6 is 10, so that's neons. I'm doing math here, okay? So let's do that, and let's figure out what potassium, actually tell me right now, who does potassium want to look like? Huh? Well, it could look like anybody, but like let's go with the chemistry here. It wants to look like argon because potassium I wish I had like 13 periodic tables up here. Potassium, which is over here, can either take that one electron, one valence electron that it has, one VE, one valence electron that it has, and it can lose it, and it can backtrack itself to look like argon. Or it can gain 1, 2, 3, 4, 5, 6, 7, 8, 9, 15 electrons to look like krypton. Which is easier? Right. That's totally like you want to go the shortest distance to your noble gas, and then you don't want to work hard to look cool. You want it to happen fast. So you got to go from potassium to argon. So potassium's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and that's it. So the ions we need to be familiar with because they are losing and gaining to look like a noble gas's electron configurations. Copper, though, copper is a little different. It's in the middle of the transition group, okay? So that was the next example here. Copper. Okay, so copper 2. Tell me its full out electron configuration. 1s2, 2s2. Keep going. 3s2, 3p6, 4s2. Yeah, 3d. No, where's copper stop? 9. It stops at 9, okay? So, here's the deal on this one. If you are copper and you have to lose 2 electrons to be copper 2, there's only, you can try to lose both of them from 3D and make it 3D7 instead of 3D9, but this is actually the outside energy level. Why? Why is 4DS or 4s2 versus 3d10, 3d9? Why is that one the outside energy level? Yeah, it's the highest energy level. It's a 4. That 4 means you are the 4th energy level or 4th period. It means that you're on the very outside shell. Okay, so if you were drawing on energy levels, it would be energy level 1, 2, 3, 4. These 2 electrons are here versus all these other ones that are internal. So if you're losing electrons, do you think it's easier to lose 2 on the outside or 2 on the inside? Losing the outside, and that is called the valence electron. Okay, so when you're losing electrons, you're going to lose those 2 because they are the valence electrons. And the way that I like to remember what valence means is valence means very outside. Valence, very outside. Okay, so you look for the highest coefficient, basically, which is the 4. So copper 2's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. It actually is a little, it's got some goofy changes it can make, but that's what you can stick with for now. The only difference with the 3 negative charge is that instead of losing electrons, what's happening? You're gaining them. So the last number you wrote, you're probably going to add, a specific number of electrons. So you'd add 3 electrons in that case. Okay, so try. Actually, you guys do this nitrogen one. I'm going to tell you one more example. You guys do the nitrogen one. We have memorize the first 3 or 4. We've written them a couple times, haven't we? What are they? The first couple of numbers you write? 1s2, 2s2, 2p6. I'm sorry, for nitrogen we stop at 2p what? For just straight nitrogen. Straight nitrogen, 2p3. Nitrogen ion, why 2p6? Because you added 3 electrons. Who does that look like? Neon, right? That's a noble gas. Here's how you write neon's electron configuration. Ready? If you put it in brackets and you put the symbol in it, that tells me that is you are trying to tell me neon's electron configuration. You can only do that for noble gases, okay? Because they are the cool kids. That's the electron configuration for neon. Okay? So, can we use that in some of our big, huge, long explanation ones? Yes, it is called the noble gas shortcut. Ready? Because some of that tungsten one was crazy long, right? We got time for that. Let's do it shorthand too. So let's learn how we can use our noble gas electron configurations to get the most of the work done, and then just add that little bit on the end that might describe another electron. So, hold on, let me get to that part. Noble gas. Oh, okay. Noble gas. I knew there was an easier way, right? Noble gas electron configuration. So this is exactly what I'm talking about. Argon bracket means that's the electron configuration all the way to argon. How many electrons have I taken care of so far with argon? 18. That's a lot, right? That's a whole 2 seconds, right? Okay. And then what's past this? Who am I describing? Who stops at 3d10? Zinc. So earlier we wrote out the whole 1s2, blah, 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 blah for zinc. That's also zinc. Okay? And that helps shorten up some of your electron configurations. So if you're writing an orbital diagram for that, you would write argon and then 4s up, down, 2, right? And then for the rest of it, you would write what? How many dashes? 5, and then those are all 3D, and then they would all be filled, correct? This is all the way to 10. Okay. Who is this describing? Calcium, good, because this argon is 18 electrons plus the 2 more is 20, 20 electrons, so that's 20 total, which is calciums. Okay, so that's what I wanted to make sure you guys got through today, is make sure you know how to do ions, orbital diagrams, noble gas electron configuration with shortcut and longhand. So when I say longhand, I mean the whole shebang. When I say shorthand, I mean noble gas electron configuration. Would you guys like to work on problem set 5 for a little bit and ask me questions? Yes, I'll get your questions. Who just had their hands up? I want to pull up problem set 5 for you guys real fast though. And I think that will clear up specifically this section here. And I'll come to you for individual help. And if you got it and your neighbor needs some help with that, please talk to them in your terms, because I use all those nice big chemistry terms, and sometimes you explain it easier than I do. So I'm using your knowledge. Right now, but I'm only going to give you a couple of minutes to work through it as many as you can. How many orbitals are each of the sections? I'm going to interrupt. I'm so sorry. I just told you you have all the time. This is the question that I was talking about with the terms orbital and sublevel. So remember, a sublevel is a letter, SPD now. An orbital is how many dashes you would have drawn for that sublevel. So anytime you have a P, how many P sublevel, how many orbitals are there? 3. So if I'm in the 4P, it doesn't matter. I can be in the infinity P. Doesn't matter. I'm in the P sublevel. That is 1, 2, 3 orbitals. For the D, how many? 5 orbitals. F, 7, S, 1. That's just your knowledge of the letters relationship to the number of orbitals you would draw for that. Another question. Is it good for the class? Is it not? Yes. Ask away. Ask away.
Okay, so what is it mean by when an electron is mixed with say how do you do the electron?
Oh, okay. That's actually I skipped that example. Let me do that right now for you. I was going through and figuring out where we were on notes. So if something is in the excited state, that does not mean it is an ion, right? Ions have done what with their electrons? Lost or gained, like they're kaput or there's extras. Excited state just means an electron is in a higher energy level than it should be, right? So what's calcium's normal electron configuration? Longhand. 1s2, give me more. 2p6, 3s2, 3p6, 4, S2. Stop there. There's 20. Okay, that's electron. That is the total electron configuration of calcium. Okay, but if calcium has been excited by electricity or fire, something, then it can actually take its last electron, one of them, and bounce it to a higher energy level. What's the next higher energy level? 5, right? Let's go 5s to keep it simple. So you would write this again as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's leaving one of the electrons there, and just excite one of them. The next thing would be 5s1 to show that like that's totally illegal, right? You can't just throw another electron in the next energy level if it's not filled. But when it's excited, it jumps up to the next energy level. So this right here, that last tail end, is showing that it's excited because it moved up a full energy level. But guess what? It's probably not going to be stable there for long. It's going to fall back down. And when it falls back down, it looks exactly like it did, because this is called the ground state. That's the ground state electron configuration. That's the ground state, like we talked about with the Bohr model. The lowest energy levels that all the electrons can exist in. Okay. I think that answers that question. More on here. Yeah. 2A contains a full third energy level. So I want you to find the element that has, your third energy level is consisting of 3s, 3p, 3d. 3f. 1, 2, 3, 4, 5, 6. F, that's 4f. So it's going to be whichever one has all 3s, 3p, and 3d filled. Who is that, by the way? Huh? Anybody? Who has the 3d sublevel fully filled? All 10 electrons. Zinc. Yeah, we've used zinc a lot in a lot of our examples, but that is actually zinc because it has, before the 3d is filled, you've already filled up the 3s, you've already filled up the 3d, amongst other things, like other stuff is filled, but it also has a 3d one filled. All right, if you have more questions, ask me. Maybe you guys can one minute. Sure. Okay, if you would like to continue working on problems at 5 and ask me questions, do so. If you need to finish some more data from the spec lab, which I'm thinking most of us do, I'm going to let you do that. But what I want to do is I want to collect everybody's data, because some people collect the data from parts A and B, and other people from, number 5 and 6. And we can kind of collect our data together. That is, I want to make sure you guys have data so you can do the analysis questions, and even if you don't get to it today, if you're working on problem stuff, okay? So I might just have you guys tell me numbers now where I'm on the board. Okay? So we have, we still have like 20 minutes. So if you need to go to spec 5 because you get this, then go. If you need to stay up here with me or somebody else and ask questions, stay. Okay, so you need to take a personal stand in where you are. So the labs are free. Go do what you need to do. I will put the lights down to help. Okay. Ask away. Energy level, the surge energy level, yeah, I would do the maximum. If you don't look that, there is 3 words. Period, energy level, principal quantum number, and N. They all mean the same thing. It's like, it is this. And what? Somebody's that's not that one. This is sodium is because whenever you do the 3, you do plus 2, when you drop it back to 3, you 10.
technically that 3 that you say is saying 3, even if you have a fourth period. Because you assign it to that 3, so your site will be the 3. That's what it's going to do. It's 5 electrons in the 4s, so it means like 4s, the capital S slot, right? And then 4p, 3, because 2 plus 3 is 5.
Okay,
So
so it means 5
2 is, yeah, so that's the 5 electrons in the 4s and 4p. There's, you're saying the medium? Yeah, no, that's not 4. That's not 4p.
Oh, 4P.
N is energy level, which is also usually the period number, which is also called the principal quantum number, but really it's the energy level. So N is the energy level. So if I say N1, I'll stop there. Only because of where's my remote? Because of this. And that's something I wanted to show, but I need to make sure we kind of got everybody taken care of. This is all false diagram that you would have to memorize, but nobody wants to memorize that, so I show you how to do it, right? So you know that according to off ball, you start off feeling awfully low. 1s, 2s, 2p, 3s, 3p, 4s, but then it starts crunching. It starts getting really close together at these next energy levels are filled. Energy levels and sublevels and orbitals and all that jazz. So as the 4s is filled, 4p is not next. 3d is actually in an intermediate energy level. That's why we drop away. This is all like data supported, and it's not something I made up. This is something that I just know.
How many energy levels?
Orbitals are in energy levels, not the other way. An energy level can hold 2, 5, about 8 to 15 orbitals. Energy level is just the distance you are away from the nucleus. So if you're close to the nucleus, you can only hold like 1 orbital. A little farther away from the nucleus, you can hold like 2 to 5 orbitals. If you're farther away, you can hold like 15 orbitals.
But I don't know. I think it's at home, but I think yeah.
I'll see.
Okay, thank you.
I gotta turn a couple back.
Thank you.
It's not today. You just have to suffer.
Okay.
In just a second, let me see where everybody is.
Oh, I was just wondering, was HD the real light source the one you showed us? Oh,
Yeah. Hey. Let me just quickly answer. This is problem set 5. Turn off the camera. Okay. Problem set 5. Okay. Let's go through a couple. I want to collect people's data. Leave Jesus. Talk. Well, let's ask the question. We need to. Oh, we need the board. Ty, we're going through some more of this. We need some help.
This is so stupid.
No, it's very, very complex. It's not stupid.
But that's why it's stupid.
All of these? Okay, so it contains a full third energy level. That means energy. Can you guys see the board that I write on it? Okay. It's like the third energy level consists of the 3s sublevel, the 3p sublevel, and the 3d sublevel, because it's all those sublevels that we need to. So your job is to figure out, this means that some atom has a 3s that's filled to 2, a 3p that's filled to 6. Because remember that has 3 orbitals with 2 electrons each, right? So that's 6 electrons. And then a 3d level that's filled to 10 because it's got 5 orbitals with 2 each, so that gives you 10 electrons. So really your only job is to make sure that wherever you end is ending on 3d, because you know 3d is the last tail end of that configuration. So you look on the periodic table, do you understand how to follow the periodic table along? I don't right here. So this is 1s, 2s, 3s, 4s, right? 4s, but then after that comes 3d. So the 3d is because the n minus 1
there's 3D all the way over here to 10. So zinc is the answer. Is Kindle back?
Yeah. I think you got that right.
So that's zinc right there. So you have to understand what the words mean, like sub-level, for example, or energy level. So when you're looking at B, contains only one electron in the 4p sublevel. Well, where's the 4p sublevel here? Okay, so you know this is p level, right? And then there's the 4p. That's because you counted down 1, 2, 3, 4. Which really is 1, 2, 3, 4. So if you're feeling 4, you're on 1, 2, 3, 4. You're all the way across. I'm not really doing that. That's not here. Not here. One electron. So there's our P. Yeah. 1, 2, 3. It's only one electron. I'm doing anything like D. Okay. I was just making sure. No, if I just did B, you tell me how to do C. Because they're exactly the same. Just remember, you do C. Tell me how. Just show me how. One electron in the flag.
Yeah, I think we made her.
Wait, hold on. Let me just see where you're sitting.
It's going to describe an event that one element has a full 4s. Show me where the 4 is first. That's not the 4s.
No.
So you still go 4s1, 4s2. That's going to go 2.
We should do that next time.
Because you just did the 4. Remember, this is you feel red. That's the 4s.
Oh, so it doesn't mean prime.
No, it's collectively the 5 electrons consistent, blah 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 blah. So stop there.
Oh, yeah.
Okay, so then tell me how to do that. Because remember, this is
A little fuzzy in the other side, but not like.
That's already, I've already explained that. Tie. It's not, it is because it's 1 minus 1, but it's because of this off-ball diagram. Off-ball says you filled it just like this. Lowest energy level, 1S, 2S, 2P, 3S, 3P, 4S, but then once you get up here, they start to, their energy levels are really close. So the 4S does not then go directly 4P, it goes to 2D.
So
Yes. So instead of having you memorize that, show me how to Alright, what's up, Jalen?
number 4 for the green photon.
4. Okay, so did you get the markers? And then you looked in the spectroscope and you saw the green light, right? The green line. Where did it fall?
Well, I can't give you the calculation off the top of my head.
Well, whatever it is, yeah, look at the line on there, and that line might be at like 5.5, okay? Remember, that's not 5.5 angstroms. You can multiply by 1,000, so that's 5500 angstroms. And then your job is to convert angstroms to millimeters based off of this conversion factor.
Okay.
Got it?
Okay.
Okay. looks good, so I want you to go.
Oh, so it's just like we did in number 1.
Yeah,
Oh.
exactly, yep. It's just a different source. Yeah, and so I can right off of because then you're just like, yes, peace. Just work on that for me.
All right, I'm done it.
Guys, on number 5, I'm not going to do helium. You did hydrogen and neon. If you need to get information from other people, we still have about 8 minutes left in class, but I want you to get information from the others.
Oh, yes, it is. Get all of your data today. If you don't do anything else, do it.
Oh, this song is so bright.
Yeah, no, this is the one for
One, I think I'm gonna get shot. Oh, I get it. You don't want to sit with me, okay? Actually, I should probably sit miles.
After all, I don't want to get shot.
guys, can we figure out some of these?
Well, now I have to go.
No, I'm not gonna go give somebody else something. I'm trying to get to everybody today.
Oh, yeah.
Oh wait, I should probably just write
You have 10 seconds to be back at your seats. 10, let's go. 9. 8, 7, 6, 5. Let's go. 4, 3, 2, 1. And please be quiet because I don't want to have to yell over you, okay? So tomorrow, tomorrow, listen. Tomorrow, like I said, I'm not going to be here. I'm going to let you watch a YouTube video of me teaching periodic trends. If you would like to bring a device, bring a device. I will have some computers here. Bring earphones. Bye.
All right.